Thank you very much, Victor. It's a pleasure to be with you. Thank you for the organization. Thank you for the president and the members of the Royal National Academy in Spain. And I would like to take a slightly different tack by saying that artificial intelligence can be considered quite old. After all, Hippocrates on the epidemics up here and his predecessor, Asclepius, have influenced all of Western medicine through the narratives that have still come partially to us. And I would like to argue that the biomedical science, especially in the last few years, is a incredible crucible in the sense of going too fast, that it's a unique crucible which is helping us meld together both the clinical practice, educational lessons, and scientific and ethical experimentation with this incredible technology that we have, because what we know is that we are learning tremendously from the people that went before us, starting for what is often considered almost a competitive view to artificial intelligence, which is Norbert Wiener at MIT with the development of cybernetics, which is a way of dealing with all the measurements that we can make in systems and understand not only the biological, but also human artificial systems that work with biology. And as we've heard before with the discussion of the history, what we have is an incredible process by which shortly afterwards McCarthy developed the notion of going for abstract logical models based on the general problem solving that Simon came up with. And shortly afterwards, we had the perceptron system by Rosenblatt at IBM and Cornell. And even shortly after that, in '59, Ledley and Lustig with the reasoning foundations of medical diagnosis, which led to a variety of precursors using the medical applications of Bayesian statistical reasoning, which could model both from objective laboratory and clinical data with subjective probabilities, which is itself a cognitive model of the perceptions of clinicians. All the precursors set the pace for what would become AI, because there was a major problem that understanding and reasoning with probabilities, it does not come naturally to most people, including physicians and patients. So there's a question that even though the models can bridge the cognitive logic model with probabilities, it doesn't explain it in terms of the causality of either the processes or the causality of why people are purposefully doing this, which is to take care of patients. So in 1970, I was fortunate enough to join the Rutgers University, which was starting its graduate program. And the guy who is shown there in that top picture, Saul Amarill, proposed to the National Institutes of Health they should fund a grant for the advancement of AI methods, problem-solving methods in medicine and in biology and other fields, because the NIH was largely considered at that time not to necessarily deal with clinical work, but rather with underlying biomedical research. And this was one of the motivations, together with my experience from before, having just got my degree at the University of Hawaii with a very well-known physicist and philosopher, Satoshi Watanabe, that worked on atomic physics. He was a student of de Broglie for wave theory and Heisenberg with the uncertainty principle. So I had a very interesting challenge to try to develop what turned out to be a causal model of diseases. And we were lucky with my first graduate student, Sholem Weiss, and a physician, Aaron Sapphire, at the Mount Sinai School of Medicine, to develop this model for glaucoma, which won a prize at the exhibit of the American Academy of Ophthalmology and Otolaryngology at Las Vegas in '75, because thanks to Aaron Sapphire enrolling the person, the doctor who had written the major textbook on the diagnosis and therapy of the glaucomas, Bernard Becker at Washington University. Plus, together with another bunch of specialists, we started a glaucoma consultation by computer through the ophthalmological network. And this was, as far as I know, a unique first network of physicians throughout the nation that showed that you could actually build a successful program that competed with in a gigantic, one of the big, what was then the Las Vegas Hilton that's shown in one of the James Bond movies. You could show that you could compete with experts and explain why you could arrive to diagnoses, prognoses, and treatments in this particular disease. So it was a very exciting time to be able to do this. And if you want to get a sense of why this was able to happen in the first place and why we put together the first AI in medicine workshop at Rutgers in 1975, Saul Amrell was a friend of Ed Feigenbaum, who was at Stanford. You've heard him mentioned there. Absolutely critical person in getting this started. And he was working with Joshua Lederberg on the Dendral program, which you've heard mentioned by Ted, and that was the genesis of the work on mycin 2. But all of them had been together with Herb Simon, the Nobel Prize winner in economics and AI, who had generalized the notion of human problem solving and how you can have machines, computers do it too. And at the same time, you can see the picture at the bottom there of Bill Raub from the NIH Division of Research Resources, who knew all of these people and wanted to have a way of the NIH funding a network of computers that would develop not only scientific research support through AI, but also clinical work through AI, because this was the idea of being able to do medicine, which has an impact and is impacted by science, was the key notion here. And what we have then is a crucible of people bringing cognition and perception with new ideas and willingness to develop new computational models for problem solving in biomedicine, because they had the support of very enlightened NIH administrators and the open-minded reviewers that liked what we had to say in the grants. As you've heard from my friends and colleagues, this gave rise in the 1970s and lasted through the 1980s, or essentially a historical paradigm shift, a lacune of knowledge-based reasoning and representation. And you've already seen a lot of the listings of the history before, so I won't go through the details. But essentially, the big break that we're talking about was advances not only in convolution and computational processing of text, most recently, but computational imaging, which shouldn't be underestimated because it is, in some sense, the critical extra magic sauce that goes beyond the use of language and connects us to our senses. Neural networks with reinforcement learning and being able to understand the feedback of how data and the way people process it, as well as the way statistically we can process it, turns out to be the background that led to and leads to the success of deep learning with what are now called foundational models, which are multimodal. In other words, imaging and speech, if you have it, and text, which is ideally done. And so there's an incredible number of these that one can look at and one can see reported on all the time as major successes of AI and machine learning today in medicine. Most recently, if you look at the issue just a few days ago, March 4th, the system Merlin, a computed tomography vision language foundation model, is incredibly impressive, done with a big consortium of universities and in Britain also, as well as the United States, and with a lot of data from the National Health Service in Britain. It's impressive work. But how does this pan out in terms of our understanding of what is going on? it supports the thesis that we are getting the kinds of improvements with AI for healthcare, which Topol at the University of California, San Diego, wrote a book rather anticipating a lot of this in 2019 before the ChatGPT hype. And one of Pete Solovich's colleagues, Harvard, Zach Kohane, wrote another one showing how you can apply all these GPT methods and with very good results. But this, as Topol himself pointed out in this list that I've got here, unfortunately, there's a lot of popular work that seems to suggest a lot of outlandish expectations for what it is that AI in medicine can do compared to the actual reality. Because the machine learning methodologies of the foundational multimodal models produce diagnostics and therapeutic advice, which, as we have often heard, can be quite fragile, can be unexplainable, can produce hallucinations and confabulations, and is frequently irreproducible. Just small changes in a prompt can change pretty much everything with what you see. So what are these key limitations of AI? We've heard some of them mentioned already in these foundational models that try to combine multimodal information very usefully, because after all, that's what we do as people. We're based on our sensory perception and how we learn about it in speaking with each other from the earliest days with our parents and others. Problem is, from a machine model perspective, just like for people, we're all biased. And since we're talking about generating by learning from training data, we have to understand that it is going to be almost guaranteed in any diagnostic, prognostic, or therapeutic criteria, which never really has what we would like to think of as a gold standard, which we know itself is a dubious notion in some cases, but it's a clever metaphor. All of them, however, are biased by what are current limitations in biomedical knowledge, which is continuously being updated and therefore hard to define in terms of the conceptual map that we have, or the conceptual graph or network, or ontologies, theories of reality that we think to define. And all of those are what pretty much constrain what kind of accuracy criteria we use for decisions. Therefore, clinical guidelines are also conventional approximations, not gold standards. They may be the best we have at any given time. So essentially, the advances of science and the advances in clinical practice allow us to come up with greater precision, but personalization turns out to be a very much harder prospect, because we're constantly concentrating on efficiency and evaluation of the technologies that we're developing as trade-offs as we go along in healthcare, but framing the toughest questions in clinical care with AI and its basis in cognitive science isn't at all easy. We're in the very early days still. Despite 50 years or more of experience, it's a lot of big challenges in order to bridge what can be thought of as the cognitive perceptive divide that we all think in terms of, even though it's more of a continuous spectrum. And one of the biggest challenges is individuation and the responsible action, which can only be carried out by living beings, and therefore cannot be ethically or legally automated. This is an excellent article that I recommend from the British Medical Journal on medical ethics, pointing out that serious medical actions cannot be taken algorithmically and automatically without review and integration with a final decision-making judgment of human experts who will take responsibility clinically, legally, for the ethical treatment of patients. And it's an embodied person that takes responsibility and is willing to go with the Hippocratic guidelines that Hippocratic Oath suggests. So, two key challenges for biomedicine as a crucible when you want to get everything together between humans and machines. Autonomy, individuals versus group practices. Big open question, and big challenge that faces the next generation or this generation already of how we deal in medicine with not just patients, but groups of patients, and do so in an ethical way. And automation, which is a big, difficult problem. Again, we don't have machines that can have responsibility because it's all distributed, among other things. You can ask the high-level question, how does medical evidence and information relate to these ethical behaviors for individuals and for organized groups? Making one of the main challenges personalization, which is what we hope will come from our mixture of human responsible people, practitioners, and these great technologies that help improve our medical practices thanks to biomedical research. What's a reference group similarity? It is, after all, a conventional choice, hopefully done scientifically, but it begs the question, who chooses and judges the adequacy of the reference groups of language-dependent data that we have spread over the web universally in different languages, including mathematical languages, probabilistic languages? And this is a very acute problem for clinical practice, especially for nursing, because that's where the depth of caring is most directly a personal and individual act of altruism in a world where utility theory and economics tends to rule group policies and the practical incentives and constraints of group practices in medicine. As far as I know, it's the same in Europe as in the United States, though with totally different systems. However, the same issues arise, but somewhat less acutely in biomedical research, where it's most acute in translational medicine. How are we going to decide whether a brilliant result from biomedical research, such as the new vaccines or the new treatments, are going to actually work in clinical practice? Who defines and who stays in a cohort of patients that you're studying epidemiologically? And is it indeed possible to come up with individual, personalized predictions? And unfortunately, this is, I think, a major barrier because we know that as people, we have our consciousness that is critical for us taking responsibility, having recalled through memory and perception of previous experiences what has happened in the past, and leads us to basically a socially empathetic, evidence-based medical approach to doing things. Because consciousness and memory are central to our understanding and recall of painful episodes in the past that we want to avoid in the future with feeling, and helps us bridge with empathy to others in their care. We need to explain and rationally justify it to others with responsible ethical conduct as the norms which are supported by our emotion or senses, but are bumped up to the cognitive level when we explain it to ourselves and to others. But it's something that's unique to the embodied human and how we discuss it with each other, but how, more importantly, how we feel it, and led to what can be considered in the axial age of 2,500 years ago, the absolutely central human ethical norm of to doing unto others as we would actually have done to us, and the inverse of not doing unto others what we would not have done unto us. So, key constraints in biomedicine as a crucible for AI across the cognitive perceptual divide is that human judgment in medicine requires highly perceptive cognition. And all of this is something that is not present in machines, despite the arguments in favor by my dear friend and colleague Bob. I would argue that we are unable to see our machines as being able to do human judgments with empathy and a conscious identification with others, or the fairness towards them that is necessary for assessing their clinical or related environmental health conditions, and how to act to alleviate them. In other words, I would argue that AI agents have no perception in their cognitive models because they have no conscious human perception of self and the living other. In other words, the individuations that can be defined and you can identify with. They're distributed all over the place and impossible to define machines. Clever, brilliant, but the conclusion then today that considering biomedical science as a crucible to bridge AI's cognitive perceptual divide, biomedical research where ethical concerns are not under as acute or emergency constraints, except in horrendous situations like the pandemic that we just managed to get through. Otherwise, they yield the most promising fundamental results when coupled with responsible human judgment and expertise. And so I would argue for biomedical science as a key best crucible for the future. However, for clinical work, precision medicine is what is likely to bring increasing potential of personalizing approximations through biomedical discoveries and AI technologies, but not any ultimate way of personalizing. It becomes a most challenging clinical ethical responsibility crucible. Finally, in trying to close the cognitive perceptual divide, we can only do so partially. Partially in personalization, partially in automation with efficiencies, which is the great need in a scaled up society to be able to do this, so that we can do it legally and ethically and do it in a feasible way that matches what Hippocrates suggested in the old book, The Epidemics. And it's a very challenging epidemiological and public health policy crucible. As we all know, it's one thing to ask responsibility for individuals. It is not an easy job to get consensus on responsibility for groups. So the ideal and hope is to bridge our cognitive perceptual divide and make what is currently could be described as magically meaningless combinatorial data-driven AI methods, which are these deep learning foundational models. I'm glad Pete used the word magic in his paper, because if you want to have clinically usable decision support with innovative advanced cognitive models, we're going to have to develop them much better than we have so now, because you want to be able to stay within ethical constraints driven by previous experience. And the open question is, whose and how are you going to privilege them? And in a deeper sense, can semantic or domain meaningful cross-validation methods, which are critical to being able to come with conservative estimates of what we are likely to come up with from our predictions, to understand better what is essentially an exciting, dramatic age of evolutionary human-machine systems, as Bob mentioned, with responsible reasoning and practice with empathetic care, which is the tough part, very, very hard. Which means that we need new insights and practices, experiments at the borderline between science and the humanistic practice of medicine to get new insights into the human-machine models for this, which we can call in the Internet of people and things that the Anthropocene age seems to have got us into. Thank you very much.